The content in this presentation aligns with pages 68 through 72 of your textbook, and it's meant to help you achieve Learning Objective 15, which is to discuss the basic daily cycles of temperature and compare them with the annual ones. If you haven't already done this, it's a good idea to at least skim pages 68 through 72 before you watch the video. And pay attention to the bold words, which should include the key terms listed here, but also to the figures and their captions. Please plan to read the content more thoroughly before you attempt the online quizzes. The accuracy of temperature measurement depends not only on the design and quality of the thermometers, but also on where they are placed. Placing a thermometer in direct sunlight will give a grossly excessive reading because the instrument itself absorbs solar energy much more efficiently than the air does. So placing a thermometer near a heat radiating surface like a building or the ground also yields inaccurate readings. Another way to assure a bad reading is to prevent air from moving freely around the thermometer. So where should the thermometer be placed to read air temperature accurately? The ideal instrument is in an instrument shelter like the one here. An instrument shelter is a white box with louvered sides that allows free movement of air through it while shielding the instruments from direct sunshine. Also from the ground. We don't want the thermometer to be stationed on the ground or subject to precipitation. The shelter also gets placed by convention over grass whenever possible, and as far away from buildings as the circumstances permit. The shelter has to conform to a standardized height so that the thermometers will be mounted at 1.5 meters, about 5 feet above the ground. How much do you think these conventions affect the temperature readings? On a day like today, would the temperature at the ground surface be significantly different? What if the temperature were measured outside the box? Would it be higher or lower? A look at daytime versus nighttime cooling shows us that air, being a poor conductor of heat, means that initial heating during the day is pointed mostly at the ground. So when we have a clear sunny day, the air near the surface can be warmer than the air just a meter above inside the thermometer. So when we talk about air temperatures, we're talking about the official air temperatures, which come out of the white louvered boxes. And we're not talking about the ground temperature or the air temperature between the ground surface and about 5.5 feet, which is where most of our bodies are located. So this curve shows you that the temperature in the middle of a clear sunny day will be significantly lower 5.5 feet above the ground surface than it is at the ground. At nighttime, a clear, calm night, the air near the surface may be much colder than the air above it. So the increase in air temperature with increasing height is a thermal inversion. Because that comes from long-wave terrestrial radiation, the escape of Earth's radiation, we call that a radiation temperature inversion. This series of figures is from an earlier edition of your textbook, and it illustrates how temperature near the ground changes throughout a day. At 5 a.m., the daily minimum temperature occurs because long-wave energy has been escaping from the Earth all night long. And after the sun begins to rise, the daily heating cycle will begin. Notice the difference between the temperature on the ground and the temperature just 3 feet above the ground. This schematic diagram indicates that the temperature might be as much as 10 degrees Fahrenheit. I'm also keeping track of the data as we go through these different time steps of the day. I'd like you to see the red arrow is going to show you the air temperature at 3 feet. And the green arrow will show you the air temperature at about 5.5 feet, which is where we will get our thermometer reading. Okay, so at 5 a.m., the temperature at 6 feet is just about the same as the temperature at 3 feet. Maybe a little different, but not a huge difference. It might be like 64 and 65. But I left them both at 65 in this diagram to show you that it's not a significant slope in that curve in that early hour. If you've ever done any winter camping, like I have, I spent one cold April morning, it was April in Wisconsin, is winter. I really got to feel that morning low, which occurs at 5 o'clock or 6 o'clock in the morning. It's the point where you've slept so poorly because of your body's on that cold ground that you can't stand it anymore, and you have to get up and have coffee and walk around. But here is the 5 a.m. Now let's look at the next time, which is 8 a.m. And here we have temperatures almost all matching. But notice that the ground surface has warmed a little bit more than the air directly above it. So the sun's been up for a while, although the angle of incidence, the incoming sunlight, is very low. So the heating hasn't been very intense. The temperature 3 feet above the ground hasn't changed by more than a few degrees Fahrenheit, but the ground surface temperature has increased already by 20 degrees. By 10 a.m., the air above the ground has warmed considerably, but the ground surface itself is 40 degrees warmer than it was at 5 a.m. We're still not even at the daily maximum temperature, and the amount of thermal energy being created by the ground surface itself is causing much of the temperature increase in the air above the surface. Right? And so we know this is a summer day because we're seeing ground temperatures that are close to 90. Think about what might happen on a winter day as we're going through this too. At noon, the ground temperature is about as high as it's going to get. The daily maximum temperature normally occurs shortly after the sun has reached its zenith for the day. So maybe 1 or 2 o'clock in the afternoon is the daily maximum. But this is the high temperature for this series of graphs. The temperature has increased from the low 50s in the morning at 5 a.m. to nearly 110 degrees. That's almost 60 degrees of warming. And this day isn't really much of a scorcher either, because look at the air temperatures. The air 3 feet above the ground is just over 80 degrees. By 3 p.m., notice that the air temperature above the ground has continued to climb significantly while the ground temperature has decreased by an even greater amount. The sun is past its zenith, so the ground surface, which is heating by conduction, is receiving sunlight at less than its maximum angle. And the air is being heated by convection, due to the high temperature of the ground. By 9 p.m., there's no more sunlight. So we don't have any sun adding energy to the ground surface. So the temperatures have declined significantly while the air temperature has decreased at a slower rate. This graph is the one that may be in your book. I forget if our version has this right now or not, but it's hard to look at unless you've seen it in that stepped format. So looking at this, we see a temperature maximum at 6 feet of about 85 degrees, and the daily maximum at 3 feet was about the same, but it happened at a different time. No, it didn't. I'm sorry. The surface temperature did. The surface temperature was hottest at noon, and the air temperature both at 3 and 6 feet reached their maximum at 3 p.m. And that's because the ground continues to heat the air by convection. The minimum for all of them was at 5 a.m. Look at the temperature ranges though. At 6 and 3 feet, we have very different temperatures, 20 and 21 degree Fahrenheit. But the ground surface did much more heating. So more about the type of material than the heat of the day. A quick note here on idealized daily air temperatures. Keep in mind too that the daily range of temperature continues to decrease as you go higher away from the Earth's surface, so that there's less day to night variation in air temperature near the top of a condo building than there is at the ground level. Remember also that clouds keep daytime temperatures lower and nighttime temperatures higher. That results in a smaller daily range in temperature. And in the absence of clouds, days tend to be warmer and nights are cooler, making a larger daily range in temperature. The daily variation in air temperature is controlled by incoming energy, primarily from the sun, and outgoing energy from the Earth's surface. Where incoming energy exceeds outgoing energy, we see this orange shaded area, right? This area in here. And this reflects a net surplus in energy, and the temperature rises. Where outgoing energy exceeds the incoming energy, we are in this gray region, right? So after sunset, it's all about the energy balance. After sunset, we're losing more energy than we're gaining, right? So the Earth gets to continue to radiate outward even after the sun finishes inward and the temperature begins to fall. So I wanted to show you some thermographs. These, we'll talk about thermographs a little bit more, well, how you make them in a future presentation coming up really quick. But I wanted to show you some differences between two locations that are unnamed for the time being. The difference between mediograms or thermograms for these two locations may seem pretty small at first glance, but if you look a little more closely, you can see some fairly important differences. First, if you compare the vertical, the y-axis, this location goes all the way up to 100, and this one goes only up to 90. And you can see in both cases that there's a large gap in between. But if I had to point at a maximum I would say this is the maximum for this location, and it looks like it's in the low 80s. This is the maximum for location number 2, and it seems to happen at the same time, right? The same calendar time. And it gets maybe just a little bit above 75. So this provides you a hint that the temperatures are at least a little higher in the location represented by the top graph. Let your eyes scan the red line and find those high values and low values. Did you, let's see, can you verify that these numbers are just about right? It looks to me like the 2 maximum temperatures are there in late August. And I want you to make sure you see that they look like they're 82 and about 75. These are just the daily average temperature. So we can't see any difference between the daytime, the daily high, and the nighttime, or the daily low temperatures. The top one looks more jagged though, doesn't it? Temperatures can vary a lot in this location from one day to the next, at least more so than it does in this smoother curve at the second location. Now look at the minimum temperatures. What is the temperature like during the first week of January in the top location? So the first week of January is all the way over here. We're talking about the teens, right? How about at this location? Much milder, right? Maybe 30s. In the bottom location, we can see temperatures during that first 2-week period around 45 degrees for most of the winter months, except for December. But the range for the upper chart is something like, this is the average daily temperature, mind you, between 82 and 10, 72 degrees. For the lower location, 75 and 30. So that's 40 degrees or so. 40, that's terrible math, 45 or so. Let's look, though, a little bit closer at the time periods for the annual maximum and minimum. So first we'll do the maximum, which is these last 2 weeks of August, and then we'll do the minimums, which is the last 2 weeks of December. So this is a blown up version of those 2 mediograms. With only 2 weeks of time on the horizontal scale, we can easily see daily fluctuations between high and low temperatures. At least in the upper figure, it's dramatic. That location has daily lows that dip into the high 50s overnight and daily highs that are consistently in the high 80s and low 90s. The range for this 2-week period is about 30 degrees or so. At the other location, the lower graph, we can in fact see daily highs and daily lows. However, they're nowhere near as consistent as they were at the other location. So here's a daily low, here's a daily high, right? And also, here's a daily low, and here's a daily high. So the variation may be pretty significant, or it may not be that much. And over here, I see a very predictable daily range of temperatures. Let's see, you can imagine people living at the location, bottom location, on the night of the 18th and the 19th, where I just drew that arrow, felt unusually warm, right? You can also see that while the daily high temperatures at this location are just as high as they were at the top location on the 18th and the 19th, and also the 24th and the 25th and the 26th, right? The average daily high has to be lower for this 2-week period in the bottom location, right? The range for the 2-week period is between 45 and 92 degrees Fahrenheit or 47 degrees. So the top location is consistently warm, and the bottom location is having waves of high temperature, right? So here's one wave, and here's another wave. But this one is, one day is a little bit warmer than the cooler phase. We might be down to a high of 78 on one day, but a fairly consistent summer temperature. Comparing the temperatures in December, we see that the coldest temperatures of the year occur in the top location early in the morning of the 17th and 18th of December, when the temperatures drop to just above 0 degrees Fahrenheit. The daily cycle of warming and cooling is less pronounced during this time range, but the range of temperatures is about 40 degrees. At the lower location, Christmas night is about the lowest temperature for that time period. And you can see that those temperatures, which are kind of hidden by the green dew point line, drop to about 20 degrees. The daily cycle is a little bit more visible here and possibly more pronounced during this time than it was in August, is what I mean. And the temperature range is about 30 degrees. So where are these two locations? The upper location is Wenatchee, K-E-A-T is the airport code, and the lower location is Quileute, Washington, so out on the coast. The upper graphs are east of the Cascades in the dry area, and the lower graphs are in the rainy part of the Olympic Mountains. So I hope you can see that the local radiation budget is also strongly influenced by humidity, probably by the soil type. Here I can see an area where there's an arid look to it, right? I see scree slopes and I see alluvial fans, and this looks very deserty to me. Here's sagebrush. And over here I have nothing but wetland and forest floor. So because there's less water in the atmosphere over arid regions, any water that remains in the plants in the soil is more readily removed through evaporation, especially where the soil is sandy as opposed to being full of clay. The atmosphere is also able to remove that moisture a lot more easily. Plants in arid environments become adept at retaining water through the use of these thick, waxy layers that they have. So they don't transpire as much as they do, as the plants in the wet areas do. But the dew point temperature, the green line, tells you how much cooling has to occur before condensation can occur. So you can see that in Wenatchee, we're much more likely to see condensation in fall and winter than this part of the calendar than we are in this part of the calendar, right? You can also see that kind of the opposite is true in Quileute. One other condition that can affect the daily temperature range in our state is not just whether you're on the east coast or the west side of the mountain, or on the east or the west side of the mountain range, but whether you're located on a hill or in a valley. In this diagram, you can see one of the ways that topography can affect weather. On cold, clear nights, cold air settles into the river valleys in the mountain ranges, making the valley bottoms colder than the hillsides around them. And that creates an interesting situation in which the air aloft and the air low in the valley may both be below freezing, while the air on the hillsides remains above freezing. Those regions where the temperature is above freezing are called thermal belts. If the air in the valley is colder than the air above it, it gets trapped there. There's no uplift unless the air can achieve a lower energy state by doing so. The cool air remains there until the warm air above it dissipates and allows it to rise. This is why you frequently see fog and clouds forming over rivers in the early hours of the morning. Okay, use the course content provided on the Canvas site and outside internet sources if you'd like to verify that you can formulate answers to those questions. If you can comfortably answer them, you're in great shape for the midterm. If you can't, review the textbook, rewatch the video, and see if those abilities improve. If you're still completely stumped, start a discussion on the Canvas site or ask me for help.